Today we are going to introduce the right triangle trigonometry. So everything that we will do today will be the definition of the trigonometric ratios, but for a triangle that has one angle equal to 90 degree or pi over 2. So let us remind ourselves some of the facts that we have seen in our last class, which we'll be using today as well. Remember, we defined an angle theta is acute if theta is between 0 degree and 90 degree. Or in other words, in the radian measure, I can say theta is between 0 and pi over 2. If it is equal to 0 or pi over 2 or 0 degree or 90 degree, we call them quadrant angles. Whereas an angle theta is called an obtuse angle if the angle is between 90 degree and 180 degree, and you can also write it in the radian measure by saying it is between pi over 2 and pi. Two angles, theta and phi, are coangles if theta plus phi is 90 degree, or in radian measure, equivalently one can say theta plus phi is equal to pi over 2. This coangle concept is going to be a very major concept in defining the trigonometric ratios. So let's talk a little bit about the sum of the angles in a triangle. So in any triangle, the sum of the three angles is necessarily equal to 180 degrees or pi. What is so special about a right angle triangle? Well, first and foremost, we would know that in a right angle triangle, there is a very nice relation between the lengths of the three sides of the triangle. The two sides that are the two terminal sides of the right angle, so this is at the 90 degree angle, the sides that are terminal sides of the 90 degree angle are called legs of the right angle triangle. And remember, if one of them is A, the other is B, then we know that A square plus B square is equal to C square. So let's call it leg 1. This is leg 2. And the longest side of the right triangle is called hypotenuse. So Pythagorean theorem tells us the leg 1 length square plus the leg 2 length square is equal to the hypotenuse of the triangle, length of that squared. We are going to define the trigonometric ratios on a right triangle based on a base angle. Generally, the base angle is denoted by theta. So let's start with a right angle triangle. And let's call this angle theta to be the base angle. With respect to theta, the closest terminal side of the right angle to theta is called the adjacent side. And we call it in short ADJ. The opposite side of the base angle theta, or the side that is farther from the angle theta as the terminal side of the right angle, is called the opposite side. And in short, we call it OPP. The longest side of the right angle triangle is called hypotenuse. And in short, we're going to call it HYP. With these assignments of adjacent, opposite, and hypotenuse, the ratio of two sides of these three of a right angle triangle is going to generate nice trigonometric ratios, and we will define them as follows. We will say sine of theta is the ratio of the opposite side with respect to theta over the hypotenuse, and we will read it as sine of theta. Cosine of theta will be the ratio of the adjacent side over the hypotenuse, and read this as cosine of theta. Tangent of theta will be written by tan theta, and this will be the ratio of the opposite side over the adjacent side, and as usual we will read as tangent of theta. Cosecant of theta will be written as CSC theta, and this is the ratio of the hypotenuse over the opposite side, and we read it as cosecant of theta. Secant of theta is written as ACC theta, which is hypotenuse over adjacent. As usual, we will read as secant of theta. And finally, cotangent of theta will be written as COT theta, and it is adjacent over opposite. And we read as cotangent of theta. So these are the 6 trigonometric ratios basic definition for a right angle triangle. Now we are going to notice one very nice information about this right angle triangle. Instead of calling this angle as my base angle theta, one might have chosen this angle on the top as the base angle theta. So note that with respect to this base angle, whatever was adjacent is now the opposite side, because this is the side on the further side from theta. Whatever was opposite has become the adjacent side, and the hypotenuse is remaining the hypotenuse. So with respect to this theta, if I now define sine, I have to do opposite over hypotenuse, but that was adjacent over hypotenuse in my previous situation. So depending on the choice of the base angle in a right angle triangle, sine and cosine, they refer to the same trigonometric ratio. So whatever was opposite over adjacent for theta, being the angle referred in black, is now adjacent over hypotenuse in the angle theta referred in blue. And that's why we call these ratios are the co-ratio of each other. And why that is true? If I want to make it a little more vivid, let's call this one theta 1, and let's call the one in blue theta 2, and then see the two angles theta 1 plus theta 2 is equal to 90 degrees. So by our definition, theta 1 and theta 2 are co-angles. Why this is important? Think about sine of theta 1. That is opposite over hypotenuse. But what was opposite with respect to theta 1 is now adjacent with respect to theta 2. So I can also say this is equal to adjacent. Hypotenuse did not change, so this is adjacent over hypotenuse. But this is with respect to the angle theta 2. So that is cosine of theta 2. So since sine of theta 1 is equal to cosine of theta 2, and theta 1 and theta 2 are called co-angles of each other, the trigonometric ratios are called co of each other. And you can do the same thing for the other trigonometric ratios as well. So for theta 1, so these are all theta 1 ratios that we have defined. For theta 1 that was adjacent, now this one has become opposite. hypotenuse remained hypotenuse, but this one is sine with respect to theta 2. Similarly, for tangent, the opposite is now adjacent, the adjacent is now opposite, so this has become cotangent with respect to theta 2. If you look at cosecant, hypotenuse remained hypotenuse, but opposite became adjacent. And remember, this is secant with respect to theta 2. For secant with respect to theta 1, if I leave hypotenuse as hypotenuse and change adjacent to opposite, this has become cosecant of theta 2. Whereas cotangent, adjacent will change to opposite, and opposite change to adjacent, and whatever was cotangent for theta 1 is tangent for theta 2. So now and so on, we will remember the trigonometric ratio sine, cosine, and tangent as cosine being the co-trigonometric ratio of sine, cotangent being the co-trigonometric ratio of tangent, and cosecant being the co-trigonometric ratio of secant. And there is a very nice relationship that we're going to learn very soon between these co-trigonometric ratios. So with these information, what we're going to do now, we're going to go to our lecture note and start working on problems and learn trigonometric identities at their best. So we will learn something called Pythagorean trigonometric identity. For that, I want you to remind yourself one more time, what is the Pythagorean theorem? It says leg 1 square, but remember now we have described the right angle triangle with respect to a base angle. So say this one is the theta angle with respect to this base. I will name them adjacent, opposite, and hypotenuse. And the Pythagorean theorem will become opposite square, this is your leg 1 square, plus adjacent square, which is the leg 2 square, is equal to hypotenuse square. So we'll keep this ratio of the trigonometric identity in mind to generate other trigonometric identities. So let's go to our lecture notes. Okay, so let's remind ourselves the 6 trigonometric ratios we have defined. Opposite over hypotenuse is sine, adjacent over hypotenuse is cosine, opposite over adjacent is tangent, hypotenuse over opposite is cosecant, hypotenuse over adjacent is secant, adjacent over opposite is cotangent. So let's use it to find the 6 trigonometric ratios for the following right angle triangle. As soon as the base angle is mentioned to us, we're going to go ahead and call 12 as the adjacent side, 5 as the opposite side, and this we will find out using the Pythagorean theorem, the hypotenuse. So Pythagorean theorem tells me hypotenuse square equal to opposite square, so I can say 5 square, plus adjacent square, so now I can say 12 square. So I get hypotenuse square equal to 25 plus 144, which is 169. Then I can go ahead and take the square roots on both sides. So square root of hypotenuse square is square root of 169. Remember, square root of hypotenuse square will be absolute value of the hypotenuse, which is 13. So I get two answers. I get hypotenuse equal to 13, or I get hypotenuse equal to negative 13. But since hypotenuse is referring to the length of the side, it is always positive. So we can go ahead and say that length is always positive. So hypotenuse, we will assume, is 13 units. So this side here is 13. And the trigonometric ratios are going to follow very easily. So now I will say sine, which is opposite over hypotenuse, is 5 over 13. Cosine is adjacent over hypotenuse, so 12 over 13. Tangent is opposite over adjacent, so 5 over 12. Cosecant is hypotenuse over opposite, so 13 over 5. Secant is hypotenuse over adjacent, so 13 over 12. Cotangent is adjacent over opposite, so 12 over 5. Answers my question. The next two examples, we're going to write the trigonometric ratios for two very special angles, the 45-degree angle and the 30 or 60-degree angles. So for 45-degree angle, you recall, because the sum of all three angles in a triangle is 180, this angle being 90 degree and this being 45, that has to be 45 as well. But we are going to make this 45 in the lecture note as our base angle. So one is going to be opposite, this one is going to be adjacent, and the square root of 2 will be the hypotenuse. So we're going to write the three trigonometric ratios, sine, cosine, and tangent first. So I will say sine of 45 is your angle now. That is opposite over hypotenuse. Now, one thing we can do, we can multiply square root of 2 on top and bottom to rationalize the denominator. It's nothing, it looks better in this way. And I get square root of 2 over 2. This is a common practice in trigonometry. Cosine of 45 degree, your adjacent is 1. Hypotenuse is still square root of 2. So I can rationalize, get square root of 2 over 2. Tangent of 45 degree, whereas, is going to be opposite over adjacent, so 1. And I can write down the three other trigonometric ratios. For example, if I now going to go write cosecant of 45 degrees, that will be hypotenuse, so square root of 2, over opposite, so this is just square root of 2. Secant is going to be hypotenuse over adjacent, so still square root of 2. Cotangent will be adjacent over opposite, so still 1. As I said, the other special trigonometric value that we will learn are for the trigonometric ratios 30 degrees and 60 degrees. So let's first do it for the base angle of 60 degrees. So this is my base angle. Then square root of 3 is the opposite side, 1 is the adjacent side, and 2 is the hypotenuse. So with respect to 60 degree, I get sine of 60 degree equal to square root of 3 over 2. Cosine of 60 degrees equal to 1 over 2. Tangent of 60 degrees equal to square root of 3 over 1, which is square root of 3. So let's go ahead and write down the cosecant. So cosecant is going to be 2 over square root of 3. Cosecant of 60 degree will be 2 over square root of 3. It will be the hypotenuse over the opposite side. I can rationalize and write it as 2 over square root of 3 over 3. Secant of 60 degree is going to be 2 over 1. So that's 2. And cotangent of 60 degree is going to be adjacent 1 over square root of 3, opposite, which after rationalizing becomes square root of 3 over 3. But now what I want you to understand is, if I change the base angle in the same triangle from 60 degree to 30 degree, the sides and their lengths doesn't change. What happens with respect to 30 degree, what was opposite has become the adjacent side. What was adjacent has become the opposite side, and hypotenuse remain the hypotenuse. So how about these trigonometric values? So see, sine of 60 degrees is now opposite, so 1 over 2. I mean, this should be 30 degrees because your base angle is now 30 degrees. So let's go ahead and change it. Then cosine of 30 degrees should be adjacent, but adjacent is square root of 3. Hypotenuse is 2. Tangent of 30 degree should be opposite, which is 1 for 30 degree, and square root of 3 is the adjacent. So rationalizing will give me square root of 3 over 3. And then I will do it for cosecant of 30 degrees. Cosecant of 30 degree will be hypotenuse 2 over opposite, which is 1, and that is 2. Secant of 30 degree will be hypotenuse over adjacent, which is square root of 3 for 30 degree. Rationalizing, you get 2 square root of 3 over 3. And finally, we get cotangent, which is adjacent, so square root of 3 over opposite, and that is 1, so square root of 3. So see the relationship between the trigonometric ratios of 60 degree and 30 degree. Whatever sine was for 60 degree, cosine is the same for 30 degrees. Why? Because 60 degree and 30 degree are co-angles to each other. Similarly, whatever was cosine for 60 degree now is sine for 30 degrees. Tangent and cotangent for 60 degree and 30 degree are equal respectively. Cosecant and secant are equal for 60 degree and 30 degree respectively. Secant and cosecant for 60 degree and 30 degree respectively are equal because these are co-angles to each other. That describes two things for us. Our first observation is, since we define sine as opposite over hypotenuse and cosecant as hypotenuse over opposite, sine and cosecant are reciprocals to each other, and that gives us rise to the three trigonometric identities that are called reciprocal identities. Also, we now can formally write down the chart of trigonometric values for the spatial angles. So what I will do, I will tell you the process how you are going to help yourself remember this chart. So we'll talk about the angle theta, and angle theta spatial angles are 0 degree, 30 degrees. As soon as I say the degrees, let's go ahead and write the radian values. 30 degrees pi over 6, 45 degrees, which is pi over 4, 60 degrees, which is pi over 3, 90 degrees, which is pi over 2. For each of these spatial trigonometric ratios, angles, I'm going to find the trigonometric ratio values, and I will remember this chart. And it is not a very difficult job to remember all of these values, and I will show you how to do it for sine theta and hence create the rest of the table. So just remember the row for sine theta. Sine theta at 0 will be 0. At 30 degree or pi over 6 will be equal to 1/2. At 45 degree will be 1 over square root of 2. One can say this is square root of 2 over 2 as well, doesn't matter. At 60 degree will be square root of 3 over 2. At 90 degree will be 1. Once you have done it for sine, it's very easy to do it for cosine. Just remember, sine and cosine are co-angles to each other. What is the co-angle of 0 degree? Well, it is 90 degree. So whatever value sine was taking at 90 degree, cosine will take the same value at 0 degree. So when you are trying to find out what is cosine theta, think about what was sine of 90 degree. Well, that was 1, so this must be 1. Now I want to know cosine of 30 degree. Well, what is the co-angle of 30 degree? It is 60 degree. So cosine of 30 degree must be equal to sine of 60 degree because they are co-angles of each other. So I will go ahead and say that this is square root of 3 over 2. 45 degree is co-angle to itself. So sine of 45 degree and cosine of 45 degree will be the same. Cosine of 60 degree, 60's co-angle is 30. So cosine of 60 degree will be sine of 30 degree. So that's 1/2. Similarly, cosine of 90 degree will be sine of 0 degree because 90 and 0 are co to each other. In order to create tangent, I'm going to use sine and cosine, but to do so, I need to identify one other nice identity. Remember, tangent theta is equal to opposite over adjacent. Well, then divide opposite by hypotenuse. And since you have done the division on the top, you have to done the division on the bottom. So on the bottom, I divide adjacent by hypotenuse. But what is opposite over hypotenuse? That's sine theta. What is adjacent over hypotenuse? That's cosine theta. And that is a very nice relationship. Tangent theta is sine theta over cosine theta. Similarly, one can think about cotangent theta being 1 over tangent theta. That means a reciprocal of tangent theta. So I'm going to do the reciprocal of sine theta over cosine theta, and that will be cosine theta over sine theta. These are called quotient identities. We'll talk about them in a minute. But why this is going to help us? Well, think about tangent theta. Tangent theta is the ratio of sine over cosine. So 0 over 1, that is clearly 0. 1/2 over square root of 3 over 2. So you can cancel the two 2's and you simply get 1 over square root of 3. Do not forget that one can easily write this 1 over square root of 3 as square root of 3 over 3 by rationalizing. Whereas 1 over square root of 2 divided by 1 over square root of 2 should be equal to 1. Now, for 60 degrees, you have the ratio of square root of 3 over 2 over 1/2. Cancel the two 2's. And square root of 3 over 1 is simply square root of 3. The next one is a little difficult because it is 1 over 0. But remember, 1 over 0 is not defined because we do not know how to divide by 0. So this is undefined. Now your question would be, well, that's only the 3 trigonometric ratios, sine, cosine, and tangent. How do I know the rest? Well, also remember the trigonometric identity called reciprocal identities. What do I mean by that? So now I can go ahead and say the reciprocal of sine is cosecant. So whatever value you see at sine, flip them, write them 1 over that. So the first one becomes 1 over 0. Clearly it is undefined. Now I want to remind you, these quantities are undefined. They're not infinity. So never use infinity. Sine of 30 is 1/2. Flip it, you get 2. Sine of 45 degrees, 1 over square root of 2. Flipping it, I get square root of 2. Sine of 60 is square root of 3 over 2. So I can write it as 2 over square root of 3. Sine of 90 is 1. 1 over 1 is 1. Secant is the reciprocal of cosine. So now look at cosine and take the reciprocal. So 1 over 1 is 1. Square root of 3 over 2 is 2 over square root of 3. 1 over square root of 2's reciprocal is square root of 2. 1/2's reciprocal is 2. 0's reciprocal is going to be 1 over 0. So that will be undefined. And remember, I have one more to do now, and that is the cotangent one. So I'm going to try to fit it in here. Cotangent of theta. That will be the reciprocal of tangent. So tangent was 0. Reciprocal of 0 is again undefined. Tangent of 30 degrees is 1 over square root of 3. So reciprocal will be square root of 3. Tangent of 45 degrees is 1. 1's reciprocal is 1. Tangent of 60 degrees is square root of 3. The reciprocal will be 1 over square root of 3. Tangent of 90 degrees is undefined, or 1 over 0. The reciprocal will be 0 over 1. So that's 0. And hence what we have established is the relationship between sine, cosine, tangent, cosecant, and secant, cotangent in one table. And this table of spatial trigonometric values is going to be very important for us to remember, because we are going to refer to these spatial values throughout this course, and not only that, in your future math classes. And I told you how to simply remember it. Well, you simply remember the first row for sine, use the coangle to find cosine, use the quotient identity sine over cosine to find tangent, and then for cosecant, secant, and cotangent, you're going to take the reciprocal of sine, cosine, and tangent respectively. So keep writing this table on your own a couple of times till you feel comfortable with all these values. The next topic is understanding and recreating the Pythagorean identities. So what I do to understand it, write down the Pythagorean theorem. Remember, the form is opposite square plus adjacent square is equal to hypotenuse square. Then divide all three of these by hypotenuse square. Well, what you get when you divide opposite by hypotenuse, by definition this is sine, but because I'm squaring it, this is sine theta, but squared. Adjacent over hypotenuse is cosine theta, but square. Hypotenuse over hypotenuse is 1, so 1 square. In trigonometry, sine theta whole to the power 2 is generally written as sine square theta. Cosine theta whole to the power 2 is written as cosine square theta, and 1 square is 1. That is a Pythagorean trigonometric identity. And you can rewrite this identity by subtracting sine square from both sides, and you get cosine square theta equal to 1 minus sine square theta. Or you can subtract cosine square from both sides and get sine square theta equal to 1 minus cosine square theta. These are different forms of the same trigonometric identity. All three of them are called Pythagorean identities. I will now show you different forms of the same identity. So remember where we started. We started with opposite square plus adjacent square equal to hypotenuse square. Instead of dividing by hypotenuse, what if I divide by opposite square? All three of them divide by opposite square. Opposite over opposite is 1, so it's 1 square, but I'm going to just write down 1. And then I have adjacent over opposite. Remember, that is cotangent. So you get cotangent theta square. Instead, just write cotangent square theta. Hypotenuse over opposite is cosecant. So I get to write cosecant square theta. That is one different form of Pythagorean identity. Now you can subtract 1 from both sides and get cotangent square theta is equal to cosecant square theta minus 1. Or subtracting cotangent square theta from both sides, I get to say 1 equal to cosecant square theta minus cotangent square theta. So these three are three different forms of the same trigonometric identity known as Pythagorean identity. There is one more form. So far we have divided by hypotenuse square and opposite square. What if we start with the same identity? Opposite square, adjacent square added, giving me hypotenuse square. And now divide all three of them by adjacent square. Opposite over adjacent is tangent. So you get tangent square theta plus adjacent over adjacent is 1. Hypotenuse over adjacent is secant. So this is secant square theta. Do the same thing. Subtract 1 from both sides. So you get tangent square theta equal to secant square theta minus 1. And subtracting tangent square theta from both sides, you get 1 equal to secant square theta minus tangent square theta. So depending on the problem, we will be using one of these three equivalent forms of the same Pythagorean identity. So far, we have described 9 different Pythagorean identities. 3 involving sine and cosine, 3 involving cosecant and cotangent, and 3 involving tangent and secant. And do not forget that we have talked about 6, we can say 3, reciprocal identities. I said 6 because one can now start writing them as cosecant theta is 1 over sine theta. That's also reciprocal. Or secant theta, now you can think of as 1 over cosine theta. They're interchangeable. Or cotangent theta, you can think of 1 over tangent theta, and they are also reciprocal identities. So essentially, I have 6 reciprocal identities, 9 Pythagorean identities, and 2 quotient identities, that is tangent theta equal to sine theta over cosine theta and cotangent theta equal to cosine theta over sine theta. With the basic list of values of the special trigonometric ratios and these 17 identities, we will answer the following questions. The question tells me sine theta is 2/3, cosine theta is square root of 5 over 3. Find the value of each of the 4 remaining functions. So first I will start with tangent theta. Remember, tangent theta is sine theta over cosine theta. And that should be 2/3 divided by square root of 5 over 3. So I can cancel the 2 3's and get 2 over square root of 5. The rest of them are reciprocal identities. So cosecant of theta is reciprocal of sine, so that's 3 over 2. Secant theta is reciprocal of cosine, that's 3 over square root of 5. Now one can simply rationalize this by multiplying square root of 5 on top and bottom and write it as 3 square root of 5 over 5. And there is one more left, which is cotangent theta. which is the reciprocal of tangent. So that should be square root of 5 over 2. Answers your question. Pretty simple. The next question says sine theta is 1/2 and theta is an acute angle. So first thing, we will not understand it thoroughly right now, but we will just remember for the time being that all 6 trigonometric ratios for acute angles are positive. So our information tells us that sine theta is 1/2 and theta is an acute angle. We want to know how much is cosine theta, but we're going to use Pythagorean identity. So think about the Pythagorean identity that relates sine and cosine. There are 3 of them. Which one is the most appropriate? Is cosine square theta is equal to 1 minus sine square theta. So let's use that. So I will say cosine square theta equal to 1 minus sine square theta. So that is 1 minus sine theta is 1/2. I'm going to square it. So I get 1 minus 1/4, which is 4 over 4 minus 1 over 4, finding common denominator. So that is 3 over 4. I take the square roots on both sides. So I get square root of cosine square theta equal to square root of 3 over 4. Square root of a fraction is square root of the top. Square root of the bottom. Square root of 4 is 2. But square root of cosine square theta, I have to be careful here. It is the absolute value of cosine theta, and that is equal to square root of 3 over 2. So I actually get 2 answers out of this. Either cosine theta is square root of 3 over 2, or it is the negative of that. So I will say cosine of theta is minus square root of 3 over 2. But since theta is acute in this problem, I will say cosine theta must be positive. And that tells me cosine theta for this particular problem is going to be square root of 3 over 2, the positive value. Use the identities to find exact value of each of the 4 remaining trigonometric functions of the acute angle theta. So this is something that we have done already. So remember, we will start with tangent theta because sine and cosine are given. Tangent is sine theta over cosine theta. For us, sine theta is 5 over 7. Cosine theta is 2 square root of 6 over 7. I can cancel the 2 7s and get 5 over 2 square root of 6. If you want to rationalize, you will multiply square root of 6 on top and bottom. That will become 5 square root of 6 over 12. Square root of 6 times square root of 6 is 6. 2 times 6 is 12. Okay, so now the reciprocal identities. So cosecant theta will be reciprocal of sine, so that's 7 over 5. Secant theta is the reciprocal of cosine, so that's 7 over 2 square root of 6. Again, you can rationalize, so you can multiply by square root of 6 on top and bottom. And this is something is optional. You can or cannot. So I get 7 square root of 6 on the top. Square root of 6 times square root of 6 is 6. And then when I multiply 2 with that, I get 12. So 7 square root of 6 over 12 is secant theta. And finally, we will do it for the cotangent, which is the reciprocal of tangent. Tangent was 5 square root of 6 over 12. So I will get 12 over 5 square root of 6 again. If I wish, I can rationalize by multiplying square root of 6, and I will get 12 square root of 6 over, again, square root of 6 times square root of 6 is 6, 5 times 6 is 30. I can simplify that by dividing both 12 and 30 by 6 and get 2 square root of 6 over 5. That's my cotangent theta. The next problem is asking us to identify the proper identity, the Pythagorean identity, and answer the question without using a calculator. So pi over 12 is an angle. I don't even care how much is this angle precisely going to look like or what is the sine value of that, because I know it is an identity involving sine square and cosine square of the same angle being added. I know the value is 1. How come? So if you go back, the Pythagorean identity tells you sine square of an angle when added with the cosine square of the same angle, you get 1. There is one other trigonometric identity of this type. This is secant square 134 degrees. So remember 134 is the same angle. You are subtracting tangent square from secant square. Again, go back to the least of the Pythagorean identity. Secant square of an angle minus tangent square of the same angle is equal to 1. So even if I do not use the calculator, I know the value, and that is equal to 1. We're going to end our discussion of the trigonometry of right angle triangle here, and you will start working on your homework problems. If you have any question, you would let me know. Next time in class, we're going to generalize these concepts of trigonometric ratios for any triangle, not only for right angle triangle, for any triangle.